See if we can do this. Okay. Okay, well, we'll do it a little bit differently today. So hopefully those of you on Zoom can see this all right once I share that. Bless you. Okay. That's really bright. Okay, then. Let's see. What's on the Oh, sure. That fine. Um, yeah, let's do this. So I have a handout for you all. I think we should work on. I think it's a while. Of course, I forgot. That's really stuff. Didn't for that. The attention thing, yeah. What happens then you go away for a week? So let me, did you talk about crossbar? Interesting. Right, all right, cool. Yeah, that's, you have actually just set it down. Okay, great. All come good. So. Of course, I think I forgot. Bless you. Here's the intended for right these dogs. All right, let's get started here. So notes on lesson matrices, which just oh, that's really let's zoom back out a bit. Okay, we're good here, we're good there. Yeah, okay. I'm trying to keep this frame. All right. So some of you asked about, I forget, there's like another name for this. It's like the dynamics of vectors or something. And I was like, what's that? And then I was like, oh yeah, it's just lesson matrices. It's just another name for it. So it's really just kind of talking about how a system evolves as you keep kind of iterating from one time period to the next time period. And instead of trying to do all these kind of challenging calculations, making it into an easier thing to do by writing it as a matrix. So we're going to kind of look through this example, read through it. Hopefully I remember exactly how it goes. Let's see. So let's assume a population is divided into 3 age classes at time equals 0, where n sub x of t is the number of females of age x at time t. So this first vector here, this is just a 3x1 vector, right? It's going to look like this, or 3x1. I suppose I should say it's a vector that has 3 components, or it's a 3x1 matrix. It's really the same thing. Vectors are just matrices that are something by 1, usually a 5x1, a 4x1, or 3x1, or we can write them the other way as well. Here's the setup. Let's assume that 20% of the 0-year-old females survive to age 1, 70% of the 1-year-old females survive to age 2, and all of them die after year 2. Scientists. So here's what those things look like as equations. For the 1-year-olds next year, that's going to be 20% of the 0-year-olds this year. And for the 2-year-olds next year, that's going to be 70% of the 1-year-olds this year. And then we also talk about what the next generation is going to be. So it makes sense that for the next generation, the number of 0-year-olds equals the number of offspring from the 1-year-old and 2-year-old females. 0-year-old females are not mature enough to reproduce, and the 0-year-old males are way. Okay, I think Grant. This was written by Grant. Assume that 1-year-old females have an average of 3 female offspring, and 2-year-olds have an average of 2 offspring. So then the number of 0-year-olds next year is 3 times the number of 1-year-olds this year plus 2 times the number of 2-year-olds this year. So that's how we're writing this as equation. But so here's what we're going to do. We're going to skip this part for a second. If we start with a population of 2,000 females of age 0, 800 of age 1, and 200 of age 2, it's a lot of work to kind of go back and figure out how many of everything we have next year. So instead of doing it a less good way, we're going to write this as a matrix. So we have this 3 by 1 here of all of the amounts of different ages or 0, 1, and 2-year-old next year. And then we have the 3 by 1 matrix over here of the 0, 1, and 2-year-old amounts this year. And to get from this year to the next year, well, we're just going to do the same math. We know that the number of 0-year-olds, which is the first entry that I want to get, is going to be 0 times the number of 0-year-olds. That's a lot of zeros last year. 3 times the number of 1-year-olds last year, plus 2 times the number of 2-year-olds last year. And then for the number of 1-year-olds next year, well, the only thing that contributes to the number of 1-year-olds next year is the number of 0-year-olds that were there the year before. So it's going to be 20% times, or 0.2 times the number of 0-year-olds, and 0 of the 1-year-olds and 0 of the 2-year-olds. Similarly, for the number of 2-year-olds next year, we said that was 70% of the number of 1-year-olds last year. So that's going to be a 0 here because the 0 multiplies that, a 0.7 here, and a 0 here. So this is the matrix that gives us next year's amount of things. If you really wanted to, you could multiply it out and say, okay, it's going to be 0 times this plus 3 times this plus 2 times this. So it's exactly going to be 3n1 plus 2n2. And then the next row and column is 0.2 times n0. And then the next row and column is 0.7 times n1. So that's what we're getting next year based on what we have this year. Also, you should definitely ask questions along the way. If I'm saying something that merits clarification, please, please, please don't hesitate to do it. Hey, James, what do you mean by that? The 3 and the 2 where? Here?
Yeah.
So if we read this part again here, it's the number of 0-year-olds we're going to get next year based on how many each 1 and 2-year-old adult female is on average producing. So this is we're being told that the 1-year-old females have an average of 3 offspring. So the 3 here is multiplying by the number of 1-year-olds last year and becoming part of the number of 0-year-olds next year. Similarly, the 2 is doing the same thing for the 2-year-olds here. Other questions? Okay, we'll keep moving on, but definitely ask if you have them. So let's assume a starting population of 2,000 females of age 0, 800 females of age 0, and 200 females of age 2. How many females are in each category after 1 year? Well, that's not too terrible. We're going to take our matrix here, 0, 3, 2, 0.2, 0, 0, 0.70, and multiply it by the starting population matrix, the 3 by 1 matrix that has a 2,000 for the number of age 0s, or 0-year-olds, an 800 for 1-year-olds, and a 200 for 2-year-olds. And then we're going to do the multiplication. So rows by columns, this row multiplied by that, or I should say dotted, right? This first row dotted with this first column is going to give me 3 times 800 plus 2 times 200. Not terribly surprising because that's exactly what was described, right? The number of 0-year-olds next year should be exactly 3 times the number of 1-year-olds because each 1-year-old on average is producing 3 offspring, plus 2 times the number of 2-year-olds because each 2-year-old is on average producing 2 offspring. And then the number of 1-year-olds next year will be 0.2 times the number of 0-year-olds. And the number of 2-year-olds will be 0.7 times the number of 1-year-olds. Simplifying this out a bit, we get 2,400 plus 400, so 2,800. We get 0.2 times 2,000, which is 400. and 0.7 times 800, which is 560. And then when they ask the next question, how many females in each age category after 2 years, we would just multiply by that matrix again. So this would end up being N0 of 2 and 1 of 2 and 2 of 2. And it would equal this same matrix 0, 3, 2, 0.2, 0, 0, 0, 0.70 multiplied by this amount after 1 year that we just found. 2,800, 400, 560. Same idea. And so if we do this, and again, please, you all on Zoom, if something gets off screen, let me know because I'm kind of doing this a slightly different way. So it's less easy for me to see what's on the screen exactly. If we do this, we get, let's see, 3 times 400 is 1,200 plus 2 times 560 is 1,120. And then for the next entry, 0.2 times 2,800, which is going to be 560. Interesting. Let's write 0.2 times 2,800. And then finally, 0.7 times 400. So end up getting 2,320. Yeah, 0.2 times 2,800 is definitely 560. And 0.7 times 400 is 280. And one could keep doing this, but the numbers would start to get a little bit messy. Assuming I've done it correctly, it's the 3 times the 400 plus the 2 times the 560. All right. Continuing on. Looking at a new Leslie matrix. For the following Leslie matrix, which is this 4x4 matrix, the first question is how many age classes are there? So when we see this matrix, what I would think about doing is just assuming the number of, usually they're square, but the number of, I guess it would be the number of columns is the number of age categories we have. What I'm really thinking about is I'm going to multiply this matrix by the amount of 0-year-olds at time whatever, the amount of 1-year-olds at time whatever, the amount of 2-year-olds at time whatever. In this case, the amount of 3-year-olds at time whatever at some particular time to get the next year's amounts. That'll be N0 of t plus 1 and N1 of t plus 1 and N2 of t plus 1. I should use a pen that has a smaller tip. And N3 of t plus 1. Always multiplying the matrix by the vector to get the next year's vector or the next time iterations vector. So there's definitely 4 age classes. And then the question that's a little more interesting, what percentage of 2-year-olds survive to age 3? Well, we're trying to look at what ends up right here. So to figure out what ends up right there, we have to take the third row of our 4x4 matrix and dot it with the, that's not right. Is it right? So I said the wrong thing. So what percentage of 2-year-olds survive to age 3? I want to figure out what's end up here. How many 3-year-olds there are next year, not how many 2-year-olds there are the next year. So if we look at this fourth row dotted with this column here, you get 0 times that plus 0 times that plus 0.2 times N2 and then plus 0 times N3. So it's going to be, right, this is going to be 0.2 times N2 is going to equal next year's N3. That means 20% of 2-year-olds survive to be 3-year-olds next year. Okay. These are good questions. What is the average number of female offspring of a 1-year-old? So we're trying to figure out how many offspring a 1-year-old produces. So This first row is right. If we do this first row multiplied by this first column, I know I keep saying first column, the only column. Okay. It's going to be 1 times n zero, meaning the 0-year-olds are producing one offspring on average. 2.5 times n1, so the 1-year-olds are on average producing 2.5 offspring. 3 times n2 and 1.5 times n3. So it looks like if we're asking about what the average number of female offspring a 1-year-old produces, that's going to be 2.5 because the 2.5 is multiplying by the number of 1-year-olds to give you 0-year-olds next year. Continuing on. Now this one, I think you also do this one. Assume that a population is divided into 4 age classes and that 65% of females of age 0, of the females of age 0, 40% of the females age 1, and 30% of the females age 2 survive until the end of the next breeding season. Additionally, assume that females age 1 have an average of 3 female offspring, females age 2 have an average of 7, females age 3 have an average of 4. So I want you all to try and draw correctly the 4x4 matrix. Then you multiply it by I'll stop talking. You guys should just try and do the matrix. From somebody. And then 30 seconds. Then we'll start talking about it. All right, let's take a look. One thing I'll say about these questions is I always feel like the I always want to start with the first row, but that's usually the last information they give you. Usually they tell you like the survival rates for each thing to the next year is kind of like not that. What the first row is always how many new offspring you're going to get. So the first row here, I'm really looking at the last sentence here. Females age 1 have an average of 3 female offspring. So that means I want to have a 1 right there. So, oh, sorry, not a 1, a what? A 3. So that my females of age 1 produce 3 offspring each next time or next year for the next year. And then females age 2 have an average of 7. Seems like a lot. There you go. And then females age 3 have an average of 4. So you multiply this or dot this row with this column, you get 0 times the 0-year-olds plus 3 times the 1-year-olds plus 7 times the 2-year-olds plus 4 times the 2-year-olds to get next year's 0-year-olds. And then I always think about how this next part essentially is always all the values are one slot or step below the main diagonal. Like that's just how it always works out. So I am being told that 65% of the females age 0 make it to be age 1. So I need to have a 0.65 right here. So that 0.65 times and 0 is going to end up in this second entry in my resulting vector here. And then I should have 0, 0, 0 here. So 65% of the 1-year-olds of the 0-year-olds become 1-year-olds, and then none of the other ones become 1-year-olds next year, right? Only the 0-year-olds can become 1-year-olds next year. And similarly, only the 1-year-olds can become 2-year-olds next year, and only the 2-year-olds can become 3-year-olds next year. So the percentage of 1-year-olds to become 2-year-olds is 40%. And the percentage of 2-year-olds to become 3-year-olds is 30%. That's what our matrix looks like. Yeah.
Sorry, when they asked to expand your matrix diagram, does that include like the three like slots or just like the main one?
When you say the slots, I'm not sure what you mean exactly.
Like,
Oh no, you just need this one. You just need the 4x4 or the 3x3 or whatever. It's typically a square matrix, whatever that matrix is. You don't need these two. But I like writing them to help me remember what's going in and what's coming out. Because it helps me see, oh yeah, I'm trying to figure out what's going here. I want to use the second row here with the only column I have here. It's a really good also reminder that the row of your first matrix dotted with the column of your second matrix gives you that row and column entry in your resulting matrix. So I knew that to get the entry that's in the second row only column, I had to use the second row here and the first column here. I had no other choice. And it always works out that way. If at time 0, okay, I feel like this question is not super. Oh wait, let's read it just to be sure. If at time 0 the population consists of 1,500 females, age 0, 500 age 1, 250 age 2, and 50 age 3, find the Leslie matrix and age distribution at time 2. We already found the Leslie matrix, so we would just multiply by that twice. I don't think we need to do that. I don't want to do that. Is what I'm really saying. I want us to move on to the next thing. So you all should do that on your own. Take this matrix, which I'll call L. And you should find L times 1,500, 500, 250. By the way, I'll point out that I have posted the solutions to this handout on Canvas. So whatever we don't get to or whatever you want to look at more carefully, it's already there to see. You should do this on your own and then go look and see if you've done it right. Moving along. So there's a little bit more to this sometimes where we make these matrix diagrams that kind of help you construct the matrix. I don't think they're super duper necessary, but some people really like them. Let's go ahead and read through this example to kind of see what's going on here. Consider a population of women at risk of developing breast cancer. Each individual's health status can be in one of 3 states: healthy, early state, or late state. So for each of the states, we're going to draw essentially a little circle. So we'll say healthy, say, sorry about early and late. Each year, 0.3% of healthy women develop early stage disease. So that means of the healthy women, 0.3% of them, so not the number 0.3, but 0.003, right? Yeah. Move from being healthy to being early. Similarly, 68% of women with early stage disease recover through treatment. So, sorry, let's read that again. 68% of women with early stage disease recover through treatment. So we have 60% of the early stages going back to healthy. And 32% of them develop late stage. So you can't stay early, apparently. right? You either go from early to healthy or early to late. There's no other option in this model, right? Like not really in real life, just like in this model, that's what's happening. And finally, 15% of women with late stage disease revert to early stage disease. So we have, with the rest remaining in late stage. And if you look at my diagram right now, it's not correct. I've missed two very important things. And it's a little easier to contextualize if you think about the fact that emanating from any one of these three circles that represent, women having some form of disease, 100% should be going somewhere. Well, that's happening for the early ones, right? 60% going that way, 30% going that way. But for the late and the healthy, we didn't do that. What's missing here is the fact that we should have said, oh yeah, 85% of the late remain late. And in a similar way, the ones that didn't move from healthy, which are the other 99.7%, stay healthy. And we do draw little circles like this that kind of just go back to them to represent that. That's not always true in that it's not always 100% of something moving somewhere else, but in this context, it certainly is true. Okay, now we want to write the system of difference equations, which is the part I'm always the worst at, I think. So the difference equations is just meaning what do you get next year based on what you have this year for each of the different categories, in this case, all three of them. So for the healthy people next year, so h of t plus 1, well, it's going to be 99.7% of the healthy ones from this year, plus 68% of the early state disease from this year. Yeah. Sorry, my notation's not the best there. Right? So basically, everything going into the healthy circle is what should be giving us that equation. Similarly, for next year's early stage people, it's going to be, well, all the arrows pointing into it. So 0.3% or 0.003 times the current year's number of healthy people plus 0.15 times the current year's number of late stage people. And then finally, for next year's late stage people, it's going to be, well, again, all the arrows going into it. So 0.32 times the arrow coming from the E, so that plus 0.85 times LT itself. Yeah.
Subtract whatever comes out.
No, we don't. It's a good question. Yeah, I like that question, but no, we do not have to subtract everything out because when we're writing the matrix, right, well, fine, let's write the matrix and kind of see that. So it's going to be a 3x3 matrix. And again, I'll try doing it without writing. So I know that into next year's H, it should be 0.997 times this year's H and plus 0.68 times this year's E. And none of the late stage people become healthy next year. They have to travel the path of back through early and then to health. I already feel like I did myself a disservice by not writing down the vector over here. I know I said you didn't have to do that. I feel like it really helps me to see that vector being there. So I would much rather have written this. But over here, I'm multiplying by the H, the E, and the L. To me, it's like I can now visualize, oh yeah, it's going to be 0.997 times H plus 0.68 times E plus 0 times L to get the next year's H, E, and L. Same deal for the E. It's going to be 0.03 times H plus 0 times E plus 0.15 times L. And finally, for the L, it's going to be 0 times H plus 0.32 times E plus 0.85 times L. Okay, it's not too bad. Okay, let's see. In a similar way, I think you all should take the time, not right now, but to construct the matrices for each of these diagrams. It's a good exercise. It's not too challenging, but certainly will kind of get your understanding. And you'll start to see that essentially the things the things that are coming out of a thing are in the column, and things that are going into a thing are in the, so like all of this row is going to end up in your new H next year, essentially. That's the way I'm kind of end up in is not the right exact words, but that's what I'm kind of thinking about. I'm like, oh yeah, I'm doing this row by this to get my new H. Whereas this first column is essentially everything that H is contributing to the next year. So I know that in the first entry, I'm going to get 0.997 times H is going to become more H next year. And my second row column, second row multiply that's called the 0.003 times H is going to contribute to the next year's E. So the columns are kind of what each thing is contributing, and the rows are what is getting contributed to each thing next year. If that makes any kind of sense, I hope. Sounds somewhat reasonable. Okay. All right. Let's look at this last page, and we should get to those two questions over there. Oh, then you can go backwards, which actually is the thing that this is the thing that I'm much worse at is the taking the matrix and drawing the diagram from it. For me, it doesn't always want to work out. So I know here that essentially the number of rows and columns is going to be the number of circles. So here, I'm going to have circle 1, circle 2. Let's just call them A and B. Yeah, I don't love those choices, but so I'm going to write it up because otherwise I don't really know what I'm doing. So I'm going to have this matrix times A of t, B of t. So I'm going to get 1 times A plus 7 times B. And that's going to be next year's A. So 1A should be going back to itself, and 7B should be coming into A. And then next year, also, I'm going to get 4 for the second entry. I'm going to get 4 times A plus 0 times B. So 4A is going into B, but no B is going into itself. So like I was just kind of saying, each row is what's going into that thing, right? So coming into A is a 1 from A and a 7 from B. Each column is what's going out of that thing. From A, we have a 1 coming out and a 4 going out. Similar kind of logic here if you want. Call them, I don't know, A, B, and C. I know very, very exciting here. So coming out of A should be a 3, a 2, and an 8. The 3 is going back to A. The 2 is going over to B. The 8 is going over to C. Coming out of B is a 0, a 5, and a 4. 0B going to A. 5B going to itself. 4B going over to C. And then coming out of C is a 2, a 1, and a 0. Oof, not left myself a whole lot of room here. A 2 going over to A. A 1 going over to B. And nothing going back into itself. That's kind of the opposite way we've been talking about it, right? Instead of usually I would more like to think of it as what's going into each thing. Or that's what I usually do, right? So if I thought about what was coming into A next year, oh yeah, it's 3 times A plus 0 times B plus 2 times C, which is exactly what I've got. 3A going into itself, 2C going into A. And so on and so on. All right. We can hold off on this part for a second, but I don't think we have officially kind of talked about like what the inverse of a 2 by 2 matrix is. Like we might have kind of skirted it around a little bit, but let's kind of go there and then we'll get to those problems over there. So I'm sorry, I had a whole stack of paper on my desk. I'm sure it's still sitting there. Here's the lovely paper we have for now. You can't really see, that's not too terrible. We've seen worse. All right, so it should be the case that you're only going to have to find the inverse of a 2 by 2 matrix, not anything larger, not a 3 by 3. If that's not true, let me know, but it should be true. We'll talk more about that in a second. So in general, let's back it up for a second. So for a 2 by 2 matrix A, and we did actually talk about this briefly, but we should say it again. Two things. A equal to the standard kind of A, B, C, D. We have two things. One, the determinant of the matrix A, which we often write as looking like kind of an absolute value of the matrix, like that, without the little brackety parts on there. That's equal to A times D minus B times C. And then I suppose we should talk about it for a 3x3 as well, because you might get asked about a 3x3 determinant, but we'll save that for a second here. And then the inverse of A is equal to 1 divided by that determinant, AD minus BC, multiplied by, again, you switch the diagonals. So the D is there, the A is there. The off diagonals, you change the signs. So for example, and again, we should qualify here, if such a matrix, if it exists, which wholly relies on the determinant being non-zero, aka if the determinant of A is not equal to 0. This criteria has many names. The one you probably should know is that means the matrix is non-singular. I always feel like it's terrible that like the thing that has the property is that it's not the thing. But here's the way I like to remember it. Matrices that have inverses have a partner, the inverse. They're not single. They're non-singular. That's how I remember it. Non-singular matrices have a partner. They are not single. Singular matrices don't have an inverse partner. So for example, this matrix A equal to 1, 2, 3, 6 is singular. It does not have an inverse. And if you find the determinant, you will see that the determinant of A is in fact 6 times 1 or 1 times 6 minus 2 times 3, which is in fact 0. Just like the number 0 doesn't have an inverse. Matrices that have a determinant of 0 also don't have an inverse. Let's see other words here. What time is it? Okay. On the other hand, this matrix 1, 2, 3, 5 definitely has an inverse, and we can find it. And it would be 1 divided by 5 minus 6 times, and we're going to switch them up. So switch the 1 and the 5, change the signs of the 2 and the 3. And in this case, since this thing out here simplifies a lot, like 1 over -1 is just -1, I would distribute the -1 there. If it's a fraction, I tend not to distribute it. But if it's just an integer, I kind of like to. So we could write this as -5, +2, +3, -1. And you should check on your own. And I should write that this is A inverse. If you multiply these two together, you get back the identity. So in fact, let's just do it. Why don't we do it right now, James? A inverse times A is going to be -5, 2, 3, -1 times 1, 2, 3, 5. Let's see. So -5 plus 6 is 1. I mean, we shouldn't even really have to check, but we're going to check. -10 plus 10 is 0. 3 minus 3 is 0. 6 plus -5 is 1. Yep, it checks out just like we knew it was going to. Great. Okay. And then you can find determinants of larger matrices. No one should be asking you to find the determinant of anything bigger than a 3x3 because it gets the process gets messier as the matrix gets larger. We can only find determinants for square matrices. So for 3x3 matrices, there is a trick essentially that doesn't work once the matrix gets bigger. So let's look at an example here. We're going to find the determinant of a 3x3 matrix I'm about to make up. Let's say it's this one. 1, 2, -2, 0, 3, 5, 1, 6, 1. So here's how you find it. And actually you can kind of do this either way. You take your first two columns or your first two rows. People usually do it with columns. Take your first two columns and write them again. 1, 0, 1 next to the matrix. 2, 3, 6. Or if you prefer, you can take your first two rows and write them below. That'll work as well. And then you take the product of the diagonals from upper left to lower right. So 1 times 3 times 1 plus 2 times 5 times 1 plus negative 2 times 0 times 6. So if this is our matrix A, then the determinant of A that's going to be part of it is going to be plus 1 times 3 times 1, plus 2 times 5 times 1, plus negative 2 times 0 times 6, minus, then you go the other direction. Instead of from upper left to lower right, upper right to lower left. That's going to be minus negative 3 times 1, plus 1 times 5 times 6, plus 2 times 0 times 1. And then we do the calculation, and it's going to be something shocking, I know. It's going to be, let's see, 3 plus 10 plus 0 minus negative 6 plus 30 plus 0. So it's going to be 13 minus 24, which is negative 11. And that's the determinant of this matrix. Okay, we'll talk more about determinants and inverses next time, but let's go ahead and get to those two questions there because they're not too terrible and we should be able to get them both done real quickly. So let's look at the one over there that says find the second degree polynomial ax squared plus bx plus c. Oh, sorry, turn it the other way. Sorry. So p of x equal to a plus bx plus cx squared that goes through the points that passes through 0, 5, 1, 0, and negative 1, 0. Okay. And I feel like they've kind of made this one easier than it could be. The kind of long way of doing it is just to plug in all your points and get some equations. So we know that if we plug in 0, actually, I don't think it's even, I think it's not even the long way. If you plug in 0, you're going to get a plus 0, and it should equal 5. Great. A is 5. If you plug in 1, now knowing that a is 5, I'm going to get 5 plus b plus c, which should equal 0. And plugging in negative 1, I get 5 minus b, still plus c, equal to also 0. And then if I can solve the system of equations, the easiest way is just by adding these two equations together and getting 5 plus 5 plus b minus negative plus b plus negative b is 0b plus 2c equals 0. So it looks like c has to equal negative 5. And it looks like b is going to be 0. Right? If c is negative 5, then b has to be 0. So our equation is p of x equal to, I would never write it in this order, but 5 minus 5x squared. Or as I would prefer to write it, negative 5x squared plus 5. But the idea here really, so I feel like I might have skirted the intention of this problem because really what we could have done, maybe should have done, or at least thought that they thought we were going to do, is make this a matrix, right? This system of 3 equations and 3 unknowns can be thought of as a matrix. You could think of it as, okay, well, I know that it feels like it, like, yeah, I don't know. That feels like a bit more work than we really want to do. Like we know that if we're looking for A, B, and C here, then we know that 1 times A plus 0 times B plus 0 times C equals 5. We know that 1 times A plus 1 times B plus 1 times C is equal to 0. And we know that 1 times A minus 1 times B plus 1 times C is equal to 0 as well. That might have been what they were trying to get out of us as far as how you went about solving it. It's not the right way to solve it though. This is much more work than you would need to do. But if they said to say like write a matrix representing the system of equations that we would use to solve this, then this is not a bad thing to do. And actually, that kind of brings me to a bigger point, is that when we write matrices like this, they often represent systems of equations. This matrix here represents a system of 3 equations and 3 unknowns. 1 times A equals 5, 1 times A plus 1 times B plus 1 times C equals 0, and 1 times A minus 1 times B plus 1 times C equals 0. I feel like I have more to say there, but I'm trying to think like, what do you have to say about that, really? It's a good thing to remember when you're dealing with matrices, right? Because often as we move forward into 17C, we will still be doing this using matrices, specifically 2 by 2 matrices, to represent a system of differential equations, 2 differential equations and 2 unknowns. And we just don't want to lose that perspective that, oh yeah, this is what we're doing here. Okay, let's look at that last question here. Suppose that the voltage vector Vt of the heart changes from one beat to the next according to the following. You're told that the next beat's voltage is equal to 1, 0, 0, -1 times the current beat's voltage, where the voltage is supposed to be like a vector. So you can think of it as like, no, I don't want to. So if the voltage vector during the current heartbeat is 0.5, 0.1, so we're saying, great, the current heartbeat is 0.5, 0.1. What was the voltage vector in the previous heartbeat? So not V sub t plus 1, but V sub t minus 1. So we're trying to go back in time. So what we really want to think here is I'm going to rewrite this as, I guess I could just say, let's call this V sub t plus 1. So there's the next heartbeat, and I want voltage. I want to find the previous heartbeat's voltage. So I'm taking this and I'm plugging this in here. So I'm trying to solve the following equations. 0.5, 0.1 equal to 1, 0, 0, -1 times whatever the previous beat's voltage is. So you've got like, I'm going to call this V1 of t, V2 of t. Just to give the coordinates some names. Okay. I'm trying to get this vector all by itself, right? Whenever you're trying to solve an equation, you're trying to isolate the thing you're trying to solve for. How do I get this other matrix over to the other side there? Can't divide by it. What do we have to do instead? Multiply by the inverse. This is kind of a special matrix in that it is its own inverse. So if you look at this here, if my matrix A is 1, 0, 0, -1, then A inverse is 1 divided by the determinant. The determinant is 1 times -1 minus 0 times 0, which is just -1. I will point out when people talk about the determinant of a 2 by 2, they often phrase it as like I often phrase it as the product of the diagonals minus the product of the off diagonals. That is always what I am actually thinking in my head. And then we are swapping the diagonals and changing the signs of the off diagonals. But -0 is still 0, so it's still just 0 there. And if we distribute the -1, we're exactly back to where we started. So again, a somewhat atypical matrix, right? Most matrices inverses are not themselves, but this one is. So if we then multiply both sides by this matrix, and now it's really important that you multiply on the correct side here. We cannot multiply on the right. If we multiply on the right, this matrix has to go through this vector before we can get over it. In fact, it won't even be the right size, right? This product here is a 2 by 1. You can't multiply a 2 by 1 by a 2 by 2. The middle things aren't matching up. We have to multiply essentially next to the matrix that we're trying to be the inverse of. So we're going to multiply both sides on the left and get 1, 0, 0, -1 times 0.5, 0.1 equal to, we don't really need to write this up, but we're going to write it out anyway. But then we know that this is just the identity matrix, and the identity matrix times something else is just the something else. This is just equal to V1, V2. And if we actually do the multiplication over here, we're going to get 1 times 0.5 plus 0 times 0.1, so 0.5. And 0 times 0.5 plus -1 times 0.1, so -0.1. And so essentially your voltage vector is oscillating back and forth between these two vectors every time. At one heartbeat, it's 0.5, 0.1. The next heartbeat is 0.5, -0.1. And then back, and then back, and then back, and then back, and then back forever. All right. Did it. It's 2 o'clock. So I'll make sure that the previous episode, somebody asked me if like I had posted the previous things and I thought I had, but maybe I hadn't. So if you're looking for that older video, I'll go make sure that it's there. It should be on YouTube, regardless if it got posted to Canvas, but I'll make sure that it gets posted to Canvas. And hopefully this video will not be too terrible, even though the setup here has been a little bit different than usual. I think it'll be all right. And if you came to class, shouldn't affect you that much.